Hello, 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 and welcome back to Shiksha DaCosta. Today we're going to learn about functions, domain, and range. In this lesson, you'll learn what a function is as compared to a relation and how to ascertain what that function's domain and range are. And you know that you're successful or that you've done this correctly if you can explain the meaning of the term function and distinguish it from a relation. And of course, we're going to focus on linear and quadratic relations. You're also going to be able to explain the meaning of the terms domain and range. And you'll do a little investigation to represent those, and you'll describe the domain and range pretty appropriately. Finally, you'll explain what are the restrictions, if any, on the domain and range that come up from real-world situations. To start off thinking about this, let's ask yourself these questions. So Mary Lou has created an AI chatbot, and that can answer any question you feed into it. How do you think it would answer the following? Pause the video here and see if you think you can predict what the AI is going to say about these three questions. Okay, well, hopefully you were able to make a couple of guesses. And even if you'd like, you can even open up an AI language learning model or large language model and put these questions in and see what it says. When I did that, the first thing I got for the official language of Canada is actually I got English and French. These are both official languages in Canada. When I asked what was the longest river in the world, it actually gave me two answers here. It's the Nile or the Amazon. And that depends on whether we want to measure the longest river in terms of length or in terms of discharge volume. If I asked what's the freezing point of water, well, also this one gave me two answers, 0 degrees or 32 degrees. Depending if we're using Celsius, it would be 0, or Fahrenheit, then it would be 32 degrees. And that's kind of annoying, right? Like I never really got a straight answer to any of my three questions. It is extremely annoying and confusing when you ask a question and there are, in fact, two answers. Which of those is correct? Are they both correct or neither one right? For this reason, in math, we prefer a function over a relation. A relation is a way to connect two different things that we're measuring. The values of the independent variable are connected with the values of the dependent variable. But they're slightly different than a function. A function is a relation, but for something to be a function, each input can only have one output, which means if you ask someone a question, there's only one answer that they're going to give you. Sort of like that's the metaphor that we're using here. Obviously, this one is preferable for the same reason that we were kind of frustrated with those first three questions. It's always nicer to get one straight answer. Here are some comparisons on how we might see a function and how we might see a relation. So one way that we can describe a relation is with ordered pairs, and they might look like this, right? So we have coordinate pairs, x, y, x, y, x, y, x, y, within these curly brackets. And we can describe a relation, and all functions and relations could basically be described the exact same way, but what makes it a function and not a relation, or what makes this a relation and definitely not a function, so sorry, this is in fact a relation, but what makes this one not a function is the fact that there are 2 points where if we input 4, the output is a different answer. So, and that's actually true for all of these. If we look at this, and the next one we'll look at is a mapping diagram, which takes these as the inputs and gives you all of the possible outputs. So 0, if you input 0, the output is 0. And that's exactly what this says as well. You can also describe a relation using an equation. And if you're using a function, then usually instead of y, we describe it using the terminology with function notation, f at x equals the square root of x. And if we were to even put that on a graph, a function would never have two different outputs for one input, whereas in a relation that actually is possible. So what's wrong with all of these? Why aren't any of them functions? Well, in all of them, when x equals 4, what's y? Over here, you can see that there's x equals 4 twice, but y is a different value in both instances. Over here, when you input 4, you either get -2 or +2, same as this. In this equation, if we take the square root of 4, well, this is literally telling you take the positive or negative square root. And so still our answer is either 2 or -2. And finally on the graph, if we look at 4, we can see that if x is 4, y could either be 2 or -2. So in all of these, there are two different values for y for that one single value of x. Specifically, when we're looking at a graph, there is a way to tell whether something is a function or if it's a relation. It's called the vertical line test. Basically, if you can take a vertical line and sort of move it and keep it vertical, if it ever crosses a point, if it ever intersects with more than one point, and you can see right here, if I could draw a vertical line and it's actually intersecting two different points, then that basically means that for that input, there are two outputs, and that fails the definition of a function. All functions have something called domain, and we're going to take a look at that now. I'm going to ask you a question. So let's say you have a student is starting the week of school with an attention span at 100%. They're fully rested, they're ready to go. But every day that goes by, their attention span goes down a little bit further, and further, and so it goes down by about 10% per day. What do you think it's going to be on Wednesday? Pause the video here and see if you can come up with some answer. Well, hopefully you were able to say, okay, it's 80%. 100% on Monday, 90%, that's 10% less on Tuesday, and 80%, another 10% down on Wednesday. What's a day that it doesn't sort of make sense to ask this question about? Pause the video here if you need some time to think about this. What day does it not make sense to ask, what is this student's attention span? Well, hopefully you were able to come up with either Saturday or Sunday, right? If I'm asking what's the student's attention span on Saturday and Sunday, well, who cares? They're not at school, so they don't need to be attentive to anything because it's the weekend. What day or what will their attention span actually never drop to? Pause the video here and see if you can answer that. 50%, right? Because it will go down by 10% each day, but on Friday, it will reach the lowest value at 60%, and it never goes below that because after that, it's Saturday and Sunday, and then right back to Monday, they're back to 100%. If you can understand that what these questions are asking, you already sort of understand the ideas of domain and range. The domain of a function is all the different possible values for the independent variable that makes sense to you. So for in this case, what was the independent variable? The day that we are choosing to check the student's attention span. And in this case, the only values that it makes sense to use are Monday, Tuesday, Wednesday, Thursday, or Friday. Saturday or Sunday do not make sense to ask what the student's attention span is because it's the weekend, they're not in school. The range of a function is sort of related to this question. The range of a function is all the possible outputs that we can get using the values from the domain. So in this case, the range is 100%, which is on Monday, 90% on Tuesday, 80% on Wednesday, 70% on Thursday, and 60% on Friday. This is how you write the domain and range of a function. You use these curly brackets, and inside you could just write down all of the values in the domain or in the range, separated by commas. This is what the mapping diagram of that might look like. So you can see here this is the domain. This is all the possible inputs for the function. This is all the possible values that might make sense for me to ask. How attentive is the student on any given day? And the function here is telling me what the answer is for my question. So for every day, there's only one possible answer. That's what makes it a function. On Monday, they're at 100%. On Tuesday, they're at 90%, and so on and so forth. These values are called the range. Those are the possible outputs that we can get from these values in the domain. Suppose there's a computer program where you can punch in the name of a student, and it'll actually tell you what that student's average grades were from last semester. What do you think the mapping diagram might look like? You can pause the video here and draw your own mapping diagram and take a stab at it. I encourage you to do that. Well, hopefully, maybe you got something that looks like this, right? So you have a list of student names in the domain, right? We're inputting their names, and the program will give us their average. So in this case, maybe Abishan and Jimothy, they both got 100% average. Wow, smart kids. Maybe Matthew got only a 92%, and DP got an 85%. But I think I stopped here because I was like, well, am I going to list every possible name in existence? And if I do that, there's also a lot of different averages. Maybe some of them go all the way down to 0%. That makes this really too big to write out. A mapping diagram is really not the best way to do that. And even if I were to use those curly brackets and write down all of their names separated by commas, that would take forever. So very similarly, in math, sometimes there's too many numbers in the domain or too many numbers in the range. And we can't just write them out one at a time the way we see here. Instead, what we might do is use a variable to represent any number that could be in the domain or could be in the range, and then we can give that variable some rules or restrictions. So what do I mean by that? Well, let's see. For example, in the function f of x equals x squared, what values are possible to use in the domain? What sort of numbers are you allowed to multiply by themselves? The domain is going to be a number set, so I'm going to always start that with curly brackets. And in this case, well, let's see if you can think about this answer first. Don't write anything down, but I'll give you a chance to do that. Pause the video here. Well, hopefully you saw that the domain can actually be any number. Any number is allowed to be multiplied by itself. So for the function f of x equals x squared, the domain is any number that could be represented by x. And x is an element of the number set that we call real numbers. So this is what this means. We have this d here that indicates we're about to start talking about the domain. Then we start off by putting in a variable. The domain is any value that can be represented by the variable x. We put a straight line here to say to start the next rule. So we say as long as x is a real number. And that's how you write domain. The domain of this function, the only numbers that it makes sense to use are real numbers. So there's not really any restrictions. Notice that even though I could put in 1 and I could put in 2 and 3, I'm not going to write those down here because there's too many numbers to write. There's rational numbers, irrational, and these numbers even go up to and down to infinity and negative infinity, respectively. Now, before we go on to range, I'd just like to talk about this idea right here, where x is an element of the real numbers. What the heck is a real number? Maybe you forgot by now. So on number sets, there are different types of numbers that we use in mathematics. There are natural numbers, which are whole and positive, so not even zero. But every single natural number is also part of a bigger number set that we call integers. And those are whole, positive, or negative numbers. So every natural number is an integer, but integers also include negatives. All of these are part of the set that we call rational numbers. So these are fractions that have whole numbers in the numerator and denominator, and that could be a positive whole number or a negative one. And if you cannot write a number as a fraction of two whole numbers, we call that irrational, right? So some stuff like the square root of 2 or pi, those are all irrational numbers. Together, the rationals and irrationals combine for a bigger number set called the real numbers. We won't really need to worry about the one that's bigger than that, which is complex numbers. So just going back to domain and range here. So this says the domain is x in such a way that x can be any real number. So anything that's represented by a fraction, or even if it's not able to be represented by a fraction of integers. What about the range? Well, let's take a look at this function. And when I say take a look, I of course mean plot it on a graph. So here we can see, even if we look at this graph, we can see that every single number, every single point on this graph sort of corresponds to any point on the x-axis. So this means that, hey, if I'm looking for, it doesn't make sense to plug in the value -2, I can look at the graph and say like, oh, yeah, that makes sense. -2 would be like right over here, right? And so that looks like it's around 4. So yeah, it makes sense to multiply -2 by itself. The value of the function will be 4. But what are the sort of possible outputs of the function? So 4 is clearly an output, right? We can see that that's possible when the input is -2. And the way we check that it's possible is we can draw a horizontal line to the y-axis. So let me just do that from this side. So we can have possible values like 5 or 4.2 or 3.3 or 2.25 or 1.5 or 0.99999 or even just 0. All of these y values are possible depending on some x value that you might choose. What sorts of values are not possible? Pause the video here and see if you can figure some out that you will never get. Hopefully you recognize that, well, you see how the quadratic is pointing upwards on both sides, and it does go down, but it stops going down at this point. That means that it will never go below here. This is the minimum value, and all of these y values here, from 0 to -1, -2, and so on and so forth, these are never achievable. So the only values possible for the function f of x are, this is the range. These are the acceptable outputs that are possible. So the range is, this is how to read this, any value that can be represented by the function f of x. As long as f of x is greater than or equal to 0, this is the lowest number, and so any number higher than that is possible. And as long as that f of x is a real number. So just to summarize that, a function is a way to connect an input to one output. It can be expressed as a set of ordered pairs within curly brackets, a mapping diagram, an equation that uses function notation, a graph, or even a table of values, which we didn't kind of really go into too much detail today. If you want to convert that something as a function, if you find any duplicate input, so anytime the x value appears more than once, they should still lead to the same output, the same value of the dependent variable. If that's a graph, that means that the graph should pass the vertical line test. So you should never be able to draw a vertical line that touches the graph in two places. The set of all acceptable inputs is something we call the domain. So for any function, it has a domain, and those are all the numbers that it could accept. Whereas the achievable outputs, any number that it could spit out, those are called the range. And if we want to express the domain in range, we do it like this. So we put curly brackets and we can label the set as D for domain or R for range. We specify a variable that could represent all of the values that are contained in here if they're too big to write out one at a time. We put a straight line to say that we're separating a rule now. Right after that, you might place any restrictions on the variable. So you might say, okay, it has to be greater than or equal to 0. And then if you want to put another line, just keep another rule, just keep adding these vertical lines. And I wanted to add another one here that specifies the number set that the variable belongs to. So in this case, x is an element of the natural numbers. The reason that this might be different is, real life sometimes doesn't allow you to use rational numbers or irrational numbers. When you're deciding on a function's domain and range, you have to consider that real life situation. So maybe the real life calls for this to be naturals or integers. Maybe it says, maybe even though your graph extends past 0, you might say, well, I can't have a negative height, so all of my values have to be greater than or equal to 0. In this example, a special relation, which is called place at x, is designed to tell you whether a place, which is whatever you put in here for x, whether that place is a city, a state, a country, or a continent. For example, if I put in Canada, it would say, okay, Canada is a country. So if Canada is one of the possible inputs, and the function takes that and says, oh, I know what that is. That's a country, and it would tell me that. Is this actually going to be a function, or is it just going to be a relation? Well, let's see what are some of the possible inputs. I could input something like Asia. Asia is a continent. Put something like LA in. LA is a city. I can say, hey, what is Georgia? What is place at Georgia? And that right there actually would give me two different answers. Georgia is a state in the United States, but Georgia is also a country. If I put in Toronto, well, that would tell me that that's exactly a city. But if I put in something like Australia, similar to Georgia, there's actually two answers. Australia is both a country and it's the name of that continent. So that's what would make this not a function, because Georgia and Australia have two outputs for just one input. If you're asking what is Georgia, there are two answers. It's either a state or it's a country, depending on which one you're talking about. But even though you have stuff like Los Angeles and Toronto and both of them point to city, that would not disqualify it from being a function. If you have multiple inputs leading to the same output, that's actually totally fine. In this next example, pause the video here and see if you can answer this question. One of these is actually a function. Figure out which one it is, and then see if you can write down domain and range of that function. Well, hopefully you were able to look at this and be like, oh, I'm just going to do the vertical line test. And right away I can see that no matter where I move this vertical line, as long as it's between these two marks, it's always going to intersect the circle at the top and at the bottom. So it's going to have an infinite number of intersections with this circle. If I tried it out on this, again, notice here, here, and here. So in three different places, this relation fails the vertical line test. It has 2 points here, 2 points here, and 2 points here, which means that it's definitely not a function. Which sort of by process of elimination gives us this one. And this one actually definitely is a function. If I try to use a vertical line test, it never crosses or touches the function at more than one space. Sometimes it touches it in no spaces, but it has 2 points of intersections 0 times. Whereas this had 1, 2, 3 times it hit 2 points. And this one did it everywhere from -4 all the way to +2. If I want to write the domain of this or the range, remember the domain is all the x values. So if I draw just some vertical lines to see exactly what x values are possible, I'll notice that, okay, if that's -2 and that's -1, this function's largest value is -1. And so all the other values are less. So I might say the domain of this is x, that's the x-axis, in such a way that x has to be less than or equal to -1. But because this is a solid line and not a dotted line, I know that it can be any real number. It could be any decimal. What about the range? So if I do that same thing where I go horizontally from here out to the y-axis, I might see that, okay, the lowest you could go for the range is 2 right here. All the other values are above it. And because this has an arrow, it means it's going to continue in that direction. And so I might say the range is f of x, the output of x, such that f of x has to be greater than or equal to 2, but it could be any real number. In this example, this table below shows n, the number of players in a multiplayer game, and the average score that the players are able to achieve using s at n. Determine the domain and range of this. Well, this is a multiplayer game, and a multiplayer game means multiple players, which means at least 2. So for the domain, I would probably say that it looks something like this. So this says the domain is any value that can be represented by the variable n. Now, those values have to be greater than or equal to 2. That's the minimum number of players. And finally, those values have to be a natural number. They can't be a decimal. You can't have 0.3 players, right? That doesn't make any sense. You either have, or like 2 or 3. You can't have 2.3. You can't have a portion of a player. That's a murder scene. We definitely don't want that. Whereas for the range, this actually can be a piece of something greater. So the range is described by s of n such that s at n has to be greater than or equal to 0, right? Somebody could technically play this game and not touch the controller or not do anything at all, and their score would just be a blank 0. But whatever it is, the kind of answers you get from here have to be rational, right? So the range is any value that can be represented by here in such a way that this has to be greater than 0, and it has to be a rational number. Because if we're trying to find the average score for players, we would take all of the player scores, which is probably going to be a natural number, and then divide it by how many players there are. So that's a ratio of two integers. A rocket's height h at t seconds after launch is given by this equation. Find its domain and range. Now, my first step is, of course, going to be I'm going to graph this function because I'd rather not figure out anything, the long way by factoring. And if I do this, I notice that this is the quadratic that is created. I have to find its domain and range. Well, for its domain, I'm going to use the variable t, right? Because the axis down here is measuring time in seconds, t seconds, and that's the first letter of time. I'll then add the restriction. So t actually has to, even though we can see the quadratic goes below 0 and below, to the right of 6 and still below 0, it doesn't really make sense to ask sort of what was the rocket's height at -1 second or at 7 seconds? There's no way that we can sort of honestly answer that because the rocket doesn't actually go below that line. And so I might say that, okay, t is a real number as long as it's between 0 and 5.991. For the range, notice that this is a parabola. Its highest value is over here. So I'm going to say that the range is any variable, anything that can be represented by h at t in such a way that h at t needs to be between 0, so it will never go below 0, and the highest it can get to is 199.2. But it can be any real number between that because height and time are both measured using real numbers, right? You can have pi minutes or pi meters. Somebody could be pi meters tall. Is that too big? I think it's 9 feet, right? So maybe not. At the very least, we can say that h at t is an element of the reals. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice question solutions, handouts, and more on our storefront. Thanks and have a great day.